This video was requested as an educational resource for the North Carolina Business Committee for Education, or NCBCE. The goal is to share knowledge about science that's related to the COVID-19 pandemic. My name is Dr. Jared Heffron, and I serve as a microbiologist for Novozymes. Personally, I have a background in infectious diseases from my career before Novozymes, and I have experience in teaching that I've been using nearly every day for the past 20 years. Novozymes does not work in this space. However, we want students to get an opportunity to learn from my expertise and build a better understanding of the basics around what is indeed a truly unprecedented situation. My name is Dr. Jared Heffron. I'm a microbiologist with Novozymes, and today I'm going to cover a video that elaborates on the previous two videos in this series that focused on the basics of virology and virus transmission and prevention. So in this one we'll focus specifically on the COVID-19 pandemic and how those concepts play into it. I'm also joined in this presentation with a special guest, my son.
Hi!
So we're going to have a good time talking about this very interesting concept. So it's called a pandemic. We're having a COVID-19 pandemic right now. What does that mean? Well, let's start off with the word epidemic. Okay? Epidemic means that there's a disease spreading quickly in a specific community in a short period of time. And usually that specific community is like a country. So in the United States, the last time we had an epidemic was in the 2017-2018 flu season. So in the winter between 2017 and 2018, we had way more cases of flu than what's normal. And so that's an epidemic, a whole lot more than normal in one region. But if you get an epidemic that then moves across several countries, basically the whole world, just like this one is, then it becomes called a pandemic. So it's really still just an epidemic, but across a much larger area. All right. So what we're experiencing right now started out as an epidemic in China and then spread to countries all over the world and now is called a pandemic. There's two other interesting words about this that I want to talk about: endemic and outbreak. So endemic, so we have epidemic and endemic. They kind of sound similar, so be careful when you say them. Endemic means that something is just normally found in a particular place, that this is something's home. So you and I, we're endemic to the United States. When you're talking about a disease, we would say that a disease is endemic to a particular region, that it's normally circulating there. So in the United States, flu is endemic to the United States. Flu is endemic to North Carolina. And every single year, cases of flu come up. But when a whole bunch more cases than normal occurs in a very specific place, we call that an outbreak. All right? So if there are a whole bunch of cases of the flu in a school in North Carolina, we would call that an outbreak in that school. If it happened in a lot more schools in North Carolina all across the state, we would call that an epidemic. And then if that happened in schools all over the world, it would be called a
Pandemic.
Exactly, right. Right now, what we are experiencing is COVID-19 pandemic. It's already moved across the entire planet, and now we're going to talk about what that means. So in science, and especially biology, names are very important because they help communicate what we're talking about and make it clear to the rest of our audience. It helps keeps things accurate. The actual name for the virus, at least currently, is Severe Acute Respiratory Syndrome Coronavirus 2, also called SARS-CoV-2 for short. So when I say SARS-CoV-2, I'm specifically talking about the virus. The disease that most people think about, the symptoms, the way that people feel when they're sick, that is actually called coronavirus disease 2019 or COVID-19. So when we talk about people being sick, we're talking about COVID-19. COVID-19 is caused by a virus that's called SARS-CoV-2. Coronavirus is a term that you hear get tossed around a whole lot, and in truth it's inaccurate because there are 7 different strains of coronavirus, and 4 of them actually go around every single year and cause the common cold in people all over the world.
But Dad, when someone talks about the coronavirus today, they mean the coronavirus, the SARS-CoV-2 that's going around at this point right now.
Right, that's true. So in normal speech, people might say coronavirus, coronavirus, coronavirus. They mean a specific strain. But if you started talking with biologists or microbiologists, it would be good to understand there's a difference. And so the actual virus, SARS-CoV-2, and the disease is called COVID-19. But yeah, I understand. If you say coronavirus, I know what you're talking about. Whenever we're talking about the differences between different diseases, there's a couple of keywords that really are useful to help describe the different characteristics. And so here's the first couple that we're going to discuss. Infection. Infection is when a pathogen, remember anything that can cause disease, which includes viruses, when a pathogen invades a host, like my body. Okay, so if SARS-CoV-2 gets inside my body, that is the moment when I'm infected. Now, I don't usually know that I'm infected when it happens right away. You don't know until you get symptoms later, right? And you start experiencing COVID-19. Well, that period of time between infection and feeling your symptoms, that is the incubation period. So we'll talk about that in the next slide about what that looks like. But that can vary from one disease to another, and it's really important. The last word right here is contagious. Contagious means if you're talking about a virus being contagious, it means it's able to be spread from one host to the next. If you're referring to the host, you're saying if a host is contagious, it means that they are currently spreading the virus potentially to other hosts. Let's look at these terms in this chart. At the very beginning, you see the infection. And then there's a little hump that shows when people are feeling the disease symptoms. So what's that period in between infection and disease called?
The incubation period.
Right. So during that incubation period, no symptoms, but the virus is inside the host. So now I added in a few pictures into this chart just to kind of demonstrate what's going on with the host. So here at the very beginning, you get infected, a host is breathing in virus particles into their lungs. That person feels perfectly fine, doesn't even know it's happening when it happens. And then there's that incubation period where you still feel fine and healthy, right? But then the diseases start coming on and you start feeling sick. And that's when you want to stay home. That's when you want to not go to school, when you want to not go to work and you want people to leave you alone. Maybe you might go call the doctor. Now, obviously, you're contagious usually during that disease point in time because you're sneezing and you're coughing and you know that you should stay away from people and you know that people who are around you need to be washing their hands and taking care of themselves. But what's tricky is that this contagious period, or here they use the word communicability, I just added in contagious because that's what it really means. So during this contagious period, it actually can be before you start showing the disease. And you see how it's a dotted line here? It means it could be moving to the left or to the right a little bit. So you actually might be contagious for a long time before you even feel that you have the disease.
The thing that's so dangerous about this virus is its incubation period is so long and its latent period is so short. You don't know you're sick and you'll be shedding virus particles, you'll be hanging out with your friends, and then they'll get sick and shed it to other people.
Yeah, you're exactly right. You're ahead of me here a little bit, so that's perfect. Let's go to the next slide. So here's where you were skipping ahead to. This is a nice chart. We're going to visit this a couple times during this presentation, but we've got 4 different respiratory viral infections. COVID-19 is right here in the middle-ish, which is the one we care about the most right now, of course. And then there's flu, which this one happens all the time. Every single year we basically have an epidemic of flu in this country. And then these are the other 2 coronaviruses, 2 of the other coronaviruses that make people sick, SARS-CoV-1 and MERS-CoV. And here I've just highlighted the incubation time since you were bringing it up. And look, with the flu, you might know you're sick. You can start feeling symptoms within a day. Most people feel it within 2 days, actually. And with SARS-CoV-1, a lot of people know it within 2 days. Could last as long as a week. MERS, a little bit longer, 6 days. It's rough. But here, COVID-19, caused by SARS-CoV-2, minimum of 4 days, as much as 2 weeks. I mean, that's tough because it means that period of time you might be shedding the virus. And some of the research that people have done most recently indicate that actually, yes, during that incubation period, people are shedding the virus just simply by breathing, not needing the cough, not needing to sneeze. And that does have a big impact, just like you mentioned, on making this more contagious than some other diseases that we're used to. Incubation time has a big role on how infective an organism is, but also the way it infects has a very big role as well too. So right up here at the very top, it says for all these viruses, these are respiratory infections. Respiratory infections mean that they primarily infect either the upper respiratory tract or the lower respiratory tract. So that's like the throat and the bronchial tubes and the lungs. And that means that most of those get passed through the air, like droplets that come out when we cough and when we sneeze and sometimes when we breathe. Those tend to be transmitted easier, right, than something that's transmitted by touch. Like if you had a wart virus and you have to actually get the wart virus to touch broken skin on another person, right? Doesn't it just seem like it would be easier for a respiratory to transmit?
Probably.
Yeah, and it's the same too, like with, HIV is another virus that is contagious, but for that one to get transmitted into my body, I need to have a cut in my body and get blood from an infected person right into that cut, or another transmission of bodily fluids, right? And that's not going to happen as easily as just walking by someone who might be coughing, right?
Yes.
Yeah. So again, that's another reason why these kinds of viruses tend to be more contagious, because their way of being contagious is just a little simpler, and it's harder for us to protect ourselves from it. Yeah. So we were getting ahead of ourselves again. Here it is, respiratory pathogens. Spread easily in the air because of coughing and sneezing. The infection occurs because you breathe them in, or actually they might be on a surface if you put a contaminated object into your mouth or in your nose. That's why we always say, right? Don't pick your nose, wash your hands before you eat, those kinds of good things. So SARS-CoV-2 is an example of one of these. Simply breathing can actually spread it during the incubation period, like we just said. Now that we covered some basic stuff about what makes SARS-CoV-2 kind of different or interesting, let's get into more advanced specific things. We're going to use this word here, epidemiology. Can you say epidemiology?
Epidemiology.
That's close. Epidemiology, which is the study of how diseases are spread. It's a whole science within itself, within kind of infectious disease science. And so someone who does epidemiology is called an epidemiologist. All right? They are studying how diseases are spread. They're tracking when these things are being spread so that we know where it is, how much of it is there, and if we need to start worrying about preventing or changing our habits in order to protect ourselves. Epidemiologists use a couple of these other terms we're going to go over real quickly, not too much detail, but basically attack rate. Attack rate is how many people are going to get infected by this disease and going to potentially have either really extreme symptoms or even mild symptoms. All right. Then the basic reproductive number, it sounds like a long name, and then it has this abbreviation called R0. It's a little confusing because right now this term is being used a whole lot in the news. So you might hear people talk about the R0 value, the R0 value, the R0 value. What it means is that it's saying for every one person who's sick, how many other people might they pass the disease on to. And we're going to have an illustration of that a little bit later. All right. And then there's the other two terms that make a little bit more sense, the fatality rate and the hospitalization rate. So what do you think the fatality rate means?
How many people will die
Yep.
due to the disease?
That's right. How many people are going to die due to the disease? And then hospitalization rate?
How many people will go to the hospital due to the disease?
Right, exactly. And so those are usually a percentage. They're going to say a certain percentage of people might die, a certain percentage of the people will have to go to the hospital to get the proper care. We're back at this chart now, and I have blocked out SARS and MERS just to make it easier for us to make some comparisons. So let's just look about COVID-19 and flu. We already talked about incubation time, right? COVID-19 has this really long incubation time. And then that fancy epidemiological term, R0, the basic reproduction number. For every one person who's sick, how many more people might that person pass it to? So let's just go back to connecting incubation time with R0. If you have a really long incubation time, what do you think is going to happen to that R0 number?
It's probably going to go up.
All right. Why do you think it's going to go up?
Because the longer your incubation time is, the longer you're sick and shedding virus particles to other people, you don't know you're sick.
Right. Yeah, that's exactly true. And so you just have more time to interact with more people, and every one of them has a chance of getting infected, right?
Yeah.
Yeah, makes sense. All right, good. So the R naught value is higher for SARS-CoV-2 than it is for influenza virus. So influenza has a R naught value of 1.3, so it means every one person gets sick, they might pass it to 1.3 other people. Well, that doesn't make any sense because there's no 0.3 of a person floating around. So it was pretty close to 1, okay? Whereas SARS-CoV-2, for every one person who gets sick, they might pass it to 2 or 2.5 people. So I guess if we rounded that, it would be 3, right? Okay.
Yes.
Yeah, 3. So let's see what that looks like. This illustration is supposed to show an R naught value of about 2.5, basically what COVID-19 is doing right now. So we've got one person who passes it on to 3 people. It gets transmitted to 3 other people. And then of those 3, this one passes it to 2, transmits, I need to say transmits. And this one transmits it to 3, and here it's transmitted to another 3, okay? And remember, with COVID-19, this period of time can be 14 days. And during that period of 14 days, this person still doesn't even know that they're sick because they don't have the symptoms yet, right? So by the time these people are getting the disease, this person now is just starting to realize, oh no, I'm actually sick. That makes it kind of tough to track this thing, right?
Mm-hmm.
Yeah, why do you think it makes it tough to track?
Because if you are sick and have this virus, and you pass it on to 3 other people, the 3 other people don't know that they have it. They pass it on to another 8 other people. Then the first person is just starting to feel symptoms and like, oh no, I've got to warn the other people. But then by that time, it's already out of hand, and he can't track down all the people that he interacted with, all the people that they interacted with, all the people that they interacted with, so on and so forth.
Exactly. You have got it exactly right. The interaction and tracking, call it contact tracing. So that, all right, I didn't plan on talking about this, but it's a good point. Contact tracing is what epidemiologists will do. They'll say, oh no, we found out about this one case right here, and now we need to track down. They're kind of like detectives. All the people who came in contact with him, and then all the people who came in contact with that person. And that is a big part of what epidemiologists do when an outbreak is currently occurring. And they're doing that right now for dealing with COVID-19. So all these cases we hear about that are happening, they're having to figure out all the people who interacted with those people. And then they're going to have to be watching people who have symptoms. And if they have the right kind of symptoms, they got to track it into all the rest of them. But you're right. You're exactly right. It just makes this really, really hard. The longer time,
difficult.
yeah, the longer period of time between each of these transmissions and the more transmissions that can occur, it just becomes more work, right?
And it gets out of hand eventually.
Exactly. We see that here at the end. Now look, after only how many transmissions we got? 1, 2, 3, 4. 4, we got a whole bunch of people. And that's called exponential growth when I added in here at the bottom of the figure. Another thing you might hear on the news, they say something's growing exponentially. It just means that as time goes on, it keeps growing faster and faster and faster and faster. 1 becomes 3, 3 becomes 9, 9 becomes 16 or 18, or keeps going and going and going, getting bigger and bigger and bigger because it's not getting slowed down at all. Exponential growth means faster and faster growth as time continues. That was an R naught of about 2.5 for coronavirus, COVID-19, right? This is an R naught value of about 1.3, the influenza that we talked about also, okay?
Yeah.
1.3, a much lower R naught value than COVID-19. One person passes it to one person, who might pass it to one person, who might pass it to one person, who might pass it to 2 people, maybe. And the time frame for all this, remember incubation times, what was the incubation time for the flu?
2 4 days.
2 to 4 days, yeah, as opposed to maybe 2 weeks. So it's real easy if this one person gets sick to figure out how many people did I interact with, and by the time this person's getting sick, actually this one might actually start feeling symptoms as well too because it's such a shorter window of time. So it becomes a lot easier to trace who got infected, right?
Yes.
Yeah. Does this look like it gets as out of control as the COVID-19 example?
No way, not as out of control, no.
Right, exactly. So When an R naught value is below 1, meaning less than one person gets infected from another one person who's already infected, that's when we say that a disease is contained. Flu is close to 1. Even when it's at its most infectious, it's close to 1.
If we compare the flu chart to the COVID-19 chart on the previous slide, 4 hops on the influenza virus is just 4, maybe 5 people. But if we looked on the other slide, 4 hops would be over 100 people. So there's a big difference between the flu and the COVID-19 viruses.
Absolutely. Let's look at this slide one last time. We've talked about incubation time. We've talked about the R naught. Now there's these other values that we can compare as well too. Flu, case fatality rate is 0.05 to 0.1%. It's a little over 3% for COVID-19. What was fatality rate again?
How many people will die due to the disease?
Okay, that's right. And so we're saying of all the people who get sick, as many as 3% people who get it might die here, whereas only maybe 1/10 of the percent of people who get it.
It's really low for the flu.
Right. It looks and sounds low, but the more people who get sick, the bigger this number still gets. It is a percentage ultimately of who gets sick. So then let's go down and look at the community attack rate, which is what that is, right? How many people are going to potentially get attacked by it or infected? Talk about 10 to 20% of the whole population is going to get the flu in any given year, and we're looking at 30 to 40% of the population potentially getting COVID-19.
So that's almost half the population is going to get COVID-19.
Potentially, right. That's what these numbers project. And then the hospitalization rate, remember what that was?
It's how many people will go to the hospital due to the disease.
Yeah. So normally we expect about 2% of people who get influenza to have to go to the hospital, and we're thinking that it could be about as many as 19% here for COVID-19. So again, now this is always the people who get sick. In order to figure out these numbers, we have to figure out the total number of people who are getting sick, right? And then that brings us around to the other really big part of epidemiology is we got to test. Okay? We got to test. And as we test more people, these numbers change. See how there's these blue asterisks next to these numbers for COVID?
Yes.
All right, that's because this data, it says down here, is current as of March 2020, so about a month ago from when we're recording this right now. These numbers are going to change. The flu numbers, we have so much data for these going back for several decades that these numbers don't change so much anymore. But this is still so new that we're still figuring all this stuff out. And the people we know about who have this disease are the sickest people, the people who have the most extreme symptoms and cases. And we still haven't tested everybody out there, and we don't know everyone else who has that disease and all the different symptoms it might present as. We're going to mention that a little bit later here in the slide deck. So these numbers can change, and they will change. Okay, but let's get back into the testing thing.
Okay.
Testing is important. This slide is summarizing what our current test for COVID-19 looks like. I guess it's a test for SARS-CoV-2 actually. So our test for SARS-CoV-2 is, it's a respiratory pathogen, right?
Yes.
Yeah. So that means when you shed virus, it comes out of where?
Your nose.
Right.
And your mouth.
And your mouth. So when we do a test for this, you're going to get a swab up in your nose. It kind of goes a little far in there. It's not super comfortable. They have to swab your nose, and they recover the virus on the swab.
Doesn't sound too fun.
It's not too fun, but it's actually not that bad. It's definitely better than getting a shot.
Okay. I trust that.
And then we're going to recover the genetic material from the virus, its genome. Okay? And then using molecular tools, so molecular biologists and geneticists create this test that's able to screen and detect whether the genome of the virus is present. And that's where they decide whether or not it's a positive or a negative. They use this fancy technique here called RT-qPCR, which stands for Reverse Transcriptase Quantitative Polymerase Chain Reaction.
I am not going to remember that term in college.
Oh, well, I bet you can figure it out by then. Doesn't really matter what that means right now. All it is basically it's a really fancy way to detect whether DNA is present or not present. And so we do this test to determine whether the DNA, I'm going to say it's not really DNA. It's just
RNA.
It is here. You got me. You're right. It's RNA. So, but it's still nucleic acid, right? So the genome of the virus is present, and that's how they determine if somebody has a test. Do you think this test existed 6 months ago?
Nope.
No, it didn't exist 6 months ago. That means it's a brand new test. Do you think it works absolutely perfectly every time?
Not 100%.
No. Do you think it takes some time for people to figure out how to make these things work?
Probably.
Do you think then that we've been able to create enough tests to test everybody on the planet?
Nope.
Definitely not. And so that goes back to our previous slide about case fatality rate, hospitalization rate.
It's unfortunate.
Yeah, but we can only test the amount of people that we have tests available for, and we have to be careful who we test. Epidemiologists need as accurate numbers as possible, so they can't test everybody because there's a limited number of tests. They have to pick out the people who they think are most likely to have the disease. Does it mean, though, that they might miss people?
Yes.
Absolutely. And that's why those numbers, the fatality rate, hospitalization rate, the R naught, all those things can change and probably will change because we're still working this out.
And they might actually even bring in a few people that actually don't have it, and they think that they have it, but they actually don't, and they mess up, and that's fine.
Yeah.
Yes, a little bit.
And then those numbers actually tend to go down over time. So, make sense?
Sort of.
For epidemiology, what's really important?
Testing.
Exactly. So, a lot of work has been done on this virus already. Even though it is brand new. We know the entire genome sequence, and that's what this little bar chart looking map is supposed to represent. And we actually have a good prediction for what a lot of the proteins are that this genome encodes. These are three-dimensional representations of what the proteins of this virus actually look like. And that's incredibly helpful when it comes to treating the disease. That work gets done by geneticists and biochemists and molecular scientists who figure out the genome and the different proteins. All that information gets put together here where we can actually diagram what the virus looks like and what are the different sections and parts that make it up. Ultimately, this is going to be really important as we try to figure out vaccines and treatments to help treat this disease. And that work is still going on right now by those people. All that information gets put in together with what we know about the host and what the virus can do when it gets inside the host. Who's the host again?
A human lung cell.
Right. We're usually worried about this virus now getting into the human lung cells, in the lower respiratory tract. And this is a diagram of what happens. If you looked at the earlier presentation on general virus basics, then it goes through a diagram very similar to this of explaining how a virus gets into a host cell and then replicates itself, makes copies of itself, and goes out. And as it leaves the human lung cell, ultimately, what will happen is the cells will die. And all those viral particles will erupt out of it, explode. Right?
Boom.
Boom. Do you remember the fancy word for cell death?
Lice?
Lyse. That's exactly right. So the cell will lyse and all the virus particles go out. Now, if there's nothing at all present to stop the virus, it will spread into another neighboring lung cell and cause this whole problem to happen again, until eventually every single cell in your lung will lyse, or let's say my lung will lyse, and there's no lung anymore, right? That's not good for the host. The host will die, right?
They won't be able to breathe.
Nope, not at all. Fortunately, our bodies don't just let that happen. It doesn't happen because our bodies have an immune system. And the immune system is a very important system. It is a series of organs and cells in the body that all help to fight off pathogens, any kind of pathogen, whether it's a virus, bacteria, fungus. Lots of parts make it up, and so over here is a nice little list of those things like your skin and your mucous membranes inside your nose, right, just create physical barriers that prevent stuff from getting in, and they're very, very, very important. But then there's more active things that participate in there too. There's these fancy cells like dendritic cells, macrophages, basophils, neutrophils, which is one of my favorite, and these other guys, these CD4 T cells and B cells that all together help patrol your body for anything that's bad going on inside of it. All right, I'm going to try not to get into this too deep, but the immune system, immunology is the study of the immune system, and it is incredibly complicated. And immunology textbooks that I used to use when I was in school, and the ones that I've seen, they are gigantic. There's so much stuff involved with them. But let's make this as simple as we can. There are two big components to your immune system: the innate immune system and the adaptive immune system. Innate means that it's the built-in system. It's the basic system. It's not specific for any particular disease. You don't have a macrophage that specifically identifies just COVID-19, just SARS-CoV-2, and you don't have a macrophage that just identifies influenza. But it can see that there's just something weird about this virus and that it needs to do something to fight it. So most of these cells here in the innate immune system, they can fight off just about any disease, but they don't know exactly how to fight it, and sometimes they don't always recognize it right away. It takes them a little time to catch up. And the first time you ever get sick with something, those are the guys who are primarily doing the job to fight off the disease. But after you have survived your first infection, this line of defense gets really supercharged. CD4, CD8, B cells, they make up your adaptive immune system. And that's the part of your immune system that learns. And that's the part that gets specific for a certain disease. So you make B cells that are specifically good at destroying flu virus. And you make another set after having SARS-CoV-2, you make another set that's specifically good at destroying SARS-CoV-2. These guys help it so that the second time you might potentially get infected by that virus, it wipes it out really fast. And it works together with these two. So it's really important to have both. You need your innate immune system to help you last long enough to teach the adaptive immune system. And then you need the adaptive immune system to make every other time you ever get infected ever again a little easier and much quicker than the very first time it happens. Make sense?
Yes.
Yeah, it's just like when you're learning a new subject in school. You try to learn fractions, it's really daunting to start with. You don't have a lot of practice. It's like using your innate immune system. You can figure it out, but it takes a lot of time and it takes
really hard.
It's really hard. But then after you've been doing it a little while and you've been learning and you've been adapting to it, it comes easier and easier and easier. And even though maybe it's a struggle and it's not the most fun thing in the world, you get through it a little bit quicker than the very first time, right?
Mm-hmm.
Yep. So innate versus adaptive. And this is really important because have any of us, meaning humans, have any of us run into SARS-CoV-2 before a couple months ago?
No.
No.
It wasn't around. It's really new.
So everybody is fighting it using which part of their immune system? Innate or adaptive?
Innate.
Exactly. Everyone's trying to fight with the innate immune system. So does that mean it's going to take a long time for them to fight off the disease or a short time?
Longer than the adaptive.
Longer than the adaptive. They eventually need to build up an adaptive immunity. Okay? So you're exactly right. So your immune system is helping us out with that, but it's new. And so our immune system is having a challenge, and everybody is having that challenge all at about the same time within the same couple of months. Okay? All right, so let's bring it all the way back around to symptoms again. Remind me from our virus basics, the very first presentation, what leads to symptoms?
The pathogen and the immune system. The immune system fights the pathogen, and the pathogen's trying to damage your, well, not trying to damage, it's trying to make copies of itself, but it's damaging your lungs, and the immune system is coming up and hurting your lungs a little bit to fight off the pathogen.
Exactly. So this war between the two of them is causing damage in our bodies, and that's when we feel the fever. That's when we end up getting coughs, sneezing, we get tired, really tired, and because this happens in your lungs, it can get harder to breathe, right? What's really interesting about this particular disease, COVID-19, is that the range of symptoms is pretty broad. Some people, about 20% of all cases, are really the severe cases, the ones we hear about on the news, where people are having to go to the hospital and they have to get put on ventilators to help them breathe. Okay? But most people don't have it quite that bad. It still does not feel good. They are not necessarily very happy people. They don't want to deal with this, especially for how long it takes. Because some people are sick for weeks and weeks feeling like this, which is a lot longer than we're used to for the flu and for the cold, right? Because we don't have an adaptive immunity built up for these things just yet. So everyone is sick for quite a long time like this.
Yes.
Yes. And so again, this makes it much more difficult for us to deal with the disease. And this is also why those things like the incubation periods can be so long, and why the case fatality rates can be so high, and why the hospitalization rates can be so high, because no one has that adaptive immunity to help them fight this stuff off quickly. And everyone is dealing with it all at the same time, right?
In short, it's very annoying.
Now we're going to talk about, I guess, the saddest part of this whole thing. What happens in those extreme cases? Okay? On the left, this is the normal air sac of a healthy lung. And there are lots of different cells in there. Some of these are immune cells that are patrolling, looking for bad guys, and your blood vessels are going to be rolling along next to those air sacs so that oxygen can move from your lungs into your blood. And that's what keeps us alive, right? On the right is what happens when there's an infection going on. And what happens is that a lot of those immune cells start coming from your blood into the air sacs to go in and fight that war against the virus. And so what happens is a lot of damage is occurring in here right now. And in extreme cases, you'll get lungs that fill with fluid. When you have an infection down here in these air sacs, we call that pneumonia. Pneumonia is caused by a lot of different things, not just viruses. So again, pneumonia is just a description of symptoms. It's not exactly a certain kind of virus that you can catch. There's just viruses that cause pneumonia, and there's bacteria that cause pneumonia. Okay? So when you've got those symptoms, you have pneumonia, which is exactly what happens here. If you get too much fluid in your lungs, it gets really hard to breathe, because really lungs need to be dry. They need to be filled with air so they can move in and out, and your lungs can inflate and deflate. And liquid in there makes it really hard. It's basically drowning if there's too much liquid in there. All right? If people have too much liquid in there, or if their lungs are too weak, they might get tired trying to breathe on their own. If that happens, then they're not going to get oxygen into their body the way they need to anymore. If you don't have oxygen in your body, unfortunately, your organs shut down and you die. So, of course, we worry a lot about people who have problems with their lungs in the first place.
For instance, asthma, lung cancer, some other problems with lungs.
Yeah, congestive heart failure is another one like that. Yeah, anything that might cause this whole system to get a little out of control or make more fluid build up inside the lungs. Exactly.
So this brings us back to the point, why is SARS-CoV-2 such a problem?
All right. Well, let's summarize everything that we just went through, okay? It's a respiratory virus. That means it spreads pretty easily, right?
Yes.
Yep. So just by breathing around another person for long enough means you might transmit it. Long incubation time. That's a problem, right?
Because then you'd be shedding virus particles during your incubation time.
Yep, that's the next part too. You're contagious before symptoms. So before you even know it, you might be spreading it. That's a problem. Nobody, at least as of a couple months ago, nobody has an adaptive immune response to this disease. So everyone is sick for a long period of time. So when you are sick, you're taking up a lot of resources in the hospital and the doctor's offices and slowing down everything in your own home.
Yeah.
The symptoms have a wide range, from mild to moderate to serious. Some people are in the hospital and doing really badly. Some people have it really mild, so they might still be going to work, walking around, not realizing that they have a disease in them that can be incredibly dangerous for someone else. And with that long incubation time and being contagious before their symptoms, they can continue to spread it.
The one that we just talked about is probably what's so dangerous about this, am I correct?
You mean having a wide range of symptoms?
Yes.
Yeah,
Because
it is.
you don't feel very sick. Like you just have like minor cough, little bit above 98, and a bit of a drippy nose, and you're just like, oh, it's just allergies. You go hang out with your friend with asthma or something, like another 2 weeks later, and they're in the hospital with a respirator.
Yeah, you're right. That is part of the problem. So that'll bring us back around to the next video we'll do, where we'll kind of talk specifically about the treatments and the ways we deal with these diseases. But that gets into social distancing. You have to start forcing people to stay away from other people, because there's always going to be someone who barely gets affected by the disease who might still share it, spread it to someone else who has a much worse, transmit it, better word, thank you. And that person might have a much worse reaction to it, might potentially die. Exactly. And then, as of right now, again, we can't slow down this particular disease very well because we don't have any vaccines or therapeutics to treat it. So it's completely on our innate immune system to get us through this that first time through. Some people's do really well. Some people do not do quite so well. Once vaccines or therapeutics are made, that R naught value we talked about goes down. And that's a lot of why the flu R naught value is close to 1. Because we have a suite of vaccines that we give out every single year. And we have antivirals that work against the flu. But we don't have any of that stuff for SARS-CoV-2 right now.
A long time ago, the flu was a really big problem. Its death rate was like, the fatality rate was higher, and the cases were higher, and there was more people getting sick than just 1 or 2 people at a time.
Yep. And it has become less of a concern now because of our knowledge about it. So the real simple answer for why this is such a big deal is because it's new. It's new to us as a society. It's new to us as a host organism. Our immune system doesn't know what to do with it. It's new to our medical community. They don't know how to treat it. Everything about it is just quite simply new, and it results in what I've got over here on the right side of the screen. It's a disease that, because it's new, it spreads quickly. It's getting everybody sick all at the same time because it's new and we have no built-in immunities and no adaptive immune response. Some of these people are going to die, unfortunately, and that is also very, very, very bad. And we, quite simply right now, don't know how to treat the disease in the best way. And so we just have to kind of wait it out and do everything we can to prevent getting the disease and spreading the disease. And that's where you get into stuff like social distancing, which we can talk about in the next video. So that's a discussion about COVID-19 pandemic and what it's doing all across the world, what it does inside its host, why it matters, why it's hard to follow, why testing is so important. In the next video, we'll talk about the different careers and people involved with treating it, trying to figure out ways to solve this problem, either in the medical community or in our social community, and how we interact with one another. So I look forward to talking about that. Thank you so much for listening.
Thank you for listening.